All right, I want to talk to you about level curves. And first and foremost, you need to realize that level curves are just traces fixing z. So before we would take an equation and we would fix x, we would fix y, we'd fix z, and we'd get different traces, different cuts. And when you cut a 3D surface, right, you get a 2D curve. So level curves, you fix z, you get a corresponding 2D curve. These are just traces in that particular slice. Why are they called level curves? I don't know. I think maybe you could think of it as different levels of z. We typically think of z as representing height somehow. So there's z equals 1, z equals 2, z equals 10, z equals -2. Each z is a level, right? So let's do an example. So I'll just show you how you can use level curves to actually get a real accurate sense of a graph of a function of two variables. So I'll pick one hopefully you recognize instantly as a paraboloid. Let's do some of the level curves. So if we fix z equals 1, we just get the equation, right? F of xy is z. So we get the equation 1 equals x squared plus y squared. And of course, we should all recognize that's just the unit circle. Hopefully you're good to go at this point. And so something like this. And I should label, right? That's z equals 1. Then next I could do, I don't know, z equals 4, and I get 4 is x squared plus y squared, circle of radius 2, something like that. These aren't going to be perfect, but they're close enough. I could do z equals 9. I guess the point is you can just keep going, and the higher the z value, the bigger the circle. At some point we should all sort of be comfortable with this, so I'll just do that. And this is z, whoops, whoa, I had it. This is z equals 9. Okay, so you put all that together, realizing that the higher z value you pick, the larger circle you get. It's not too difficult to realize that the graph of the surface in 3 space looks something like this, right? You can sort of see each of those slices. Here's the z equals 1 slice, here's the z equals 2 slice, here's the z equals 9 slice, all giving you those circles. So level curves are super useful. We'll use them a lot. Make sure that you're comfortable. You're just slicing by fixing z's, and then the curve that you get is representing a cut. When you fix a certain z, then there's a two-dimensional cut involved. I did want to show you, it turns out that topographical maps are just level curves. So thinking of z as representing elevation. Let's switch over here. I've got a map up that of the Buffalo River. This is the Ponca region. I absolutely love hiking this area. And you can sort of see the different lines. Now, somehow our eyes pretty intuitively recognize, like I can't point very easily. Let's see if I can get my pointer. Yeah, maybe I can. No, I can't. That's okay. Our eyes somehow sort of recognize that what's up and what's down. But even if they didn't, I can't point. But if you look closely, you can see the labels of the z value. So I'm looking right by Fisher Point there in the middle of the screen. Up at the top, I see a 1700. That's saying z equals 1700. And then if I go down a little bit, I see the 1400. So that's how I can tell for sure the level curves, whether we're going up or down. Because if you go back to our example of the level curves that we did, if I erase these level curves, you could just as easily suspect that the surface actually points this way, right? If I took off labeling z equals 9, z equals 1, z equals 4, then you could imagine getting the same curves, just different z values for a paraboloid opening down. So it is important to label those. All right, well, I wanted to show you one more thing, and that's to talk about functions of 3 variables. And we need to realize that the graph of a function of 3 variables, this is a hypersurface in 4 dimensions. Now, I'm not going to lie. It's a little bit difficult to graph hypersurfaces. You can try. There's some interesting animation graphics where people sort of try to give you some sense of what something looks like. Instead of trying to graph them in 4 dimension, I want to show you how we can take slices. we can slice 4 dimensions and end up with something in 3 space that has meaning. So here's an example. Look at this example with me. We're going to think about f of xy as w. So for me, right, I use w to stand for f of xy z. Okay, and I can slice this thing. We called before, when we sliced a function of 2 variables, you got a curve, so we called it a level curve. When you slice a function of 3 variables, you get a level surface. So let's just go ahead and say fixing w gives a level surface. And so, for example, if I have w equals 1, I get 1 equals x squared plus y squared plus z squared, and this is the unit sphere. So whatever this 4-dimensional slice is, when you fix w equals 1, you get out the unit sphere. Or, for example, if I fix w equals 4, then I get out 4 equals x squared plus y squared plus z squared. And this, of course, is the sphere of radius 2. I won't write it down. The point is you recognize it. And so sometimes we're going to need to work with functions of 3 variables. Not a ton, but sometimes we will. And we're going to get back into 3 space by fixing w, by slicing and looking at level surfaces. And that's what I need you to realize, is that any surface that's generated by an equation, you can sort of solve, get a constant by itself, and think about that as actually a slice of a 4-dimensional surface. So any equation involving 3 variables you can think of as the slice of a hypersurface. So we'll talk about that a little bit later in the course. All right, that's 11.1. Let's end this thing here, and you can go on to 11.2.